This video is going to be a review. I'm going to give you all the answers to the final review for the fall semester. Okay. This is going to be a long video, and I'm not going to break it up into parts. So while you're going through, if there's a certain number that you need to find, just fast forward and try and change it so that you can find it and you don't have to sit through all of this to get to like number 13, say. Okay, we'll start with number 1. Define vector and give 3 examples of a vector quantity. To think about what a vector is, we're actually going to handle vectors and scalars at the same time. So I'm changing the question a little bit here, but I'm going to talk about scalars and vectors at once. A scalar is just a number. You guys have been doing scalars since kindergarten. I think I've said that before. An example of a scalar would be how many frogs in the bowl. And the answer to that would be just a number. You're going to get a scalar for that. A vector is a number that also has a direction assigned to it. And you guys haven't seen this before physics class probably. But an example of that would be, let's see, maybe like a velocity. I'm going 30 miles per hour, okay, or meters per second if I wrote it. That takes care of the number part. Let's say I'm going 30 meters per second and I tell you I'm going northeast. Okay, that's going to be a vector because I give you a number and a direction. So velocity is one example. Let's see, I could say that I walked 3 meters, well, I don't know, south. That would be another example of a vector. That would be a displacement vector. And finally, let's say I push 100 newtons up. That would be an example of a force vector. All right, so velocity, displacement, and force are all vectors that we've used so far this year. So let's look at number 2. Number 2 says, what is the difference between speed and velocity? Well, we just said velocity has a number and a direction. An example would be 65 miles per hour southwest. That would be a velocity. Speed, on the other hand, just has the number part. It just tells you how fast you're going. So my example here would just be 65 miles per hour. All right, number 3. We want to define a scalar. Okay, again, I've handled this already, but I'll do it again. One more time. A scalar is a quantity, is an amount that only has magnitude. Or number. When I say magnitude here, I've just used a fancy way to say number. So a scalar is a quantity that only has number. Oh, you can't see that. Here we go. Scalar is a quantity that only has number. Number 4 on our sheet. What is the slope equal to on a displacement time graph? And then on a velocity time graph. This is exactly like the example that I did in class. So if you were paying attention now, then don't worry about watching this. So here we go, a displacement time graph, and we want to know what the slope represents. So I'm going to draw 2 lines, one with a really big slope and one with a smaller slope. Now these two lines represent two different objects moving. Now how are they moving differently? What does this different slope tell us? Well, this object is going to be moving faster than this object. So the slope represents a difference in velocity. All right, if I change the slope of this line, what am I changing? I'm changing the velocity. So slope on a dt graph equals velocity. Now let's look at a velocity time graph. This one's a bit harder to see. But if you think about what a VT graph is, here's my velocity over time. If I have a slope on this line, it's changing my velocity, right? My velocity started out at 0 and is getting bigger over time. For this dotted line, my velocity again starts at 0, but it's changing at a slower rate, right? My velocity is changing at a slower rate. So slope on a VT graph equals acceleration. All right, number 5. Draw a dt graph for constant velocity, zero velocity, and acceleration. Number 6. What would a dt graph look like if the object was moving towards the left? All right, so we started out the semester, I don't know if you remember, we said that if you're moving to the right, that means you're moving in a positive direction. If you're moving to the left, what does that mean? You're moving in a negative direction. So on a displacement time graph, we're moving to the left on this graph, or our object is, so it's going to be moving towards the negative direction. So that's going to be represented with a line with a slope that's pointing in the negative direction. It's headed toward the negative numbers. It's headed towards the left. Number 7. How far does a car travel if it has a constant velocity of 35 meters per second for a time of 100 seconds? So this problem right here. What do we know? Velocity equals 35 meters per second. Time equals 100 seconds. We're solving for how far. That means distance. So let's see, where's my formula sheet? So here's my formula sheet. I want to look for a formula that uses these 3 things I've just written down. V, T, and D, and nothing else. The only thing that gives me that is this first one right here. So velocity is equal to displacement over time. I'm going to plug in the numbers that I know and leave my variable as a letter for the thing that I'm looking for. And I'm going to multiply both sides by 100. Oop. And we get that D is equal to 3,500 meters. All right, number 8. If a person walks 500 meters and it takes 250 seconds, what is the person's velocity? 500 meters is going to be my distance. 250 seconds is my time. I want to know what's the velocity. I'm going to use the same equation as before because I'm given the same variables and I'm solving for the same thing essentially. So come up with a velocity of 2 meters per second. All right, number 9. Number 9 is a little bit trickier to pick out which equation we need to use. So I really need to follow this method of writing everything down first. This car is traveling at 20 meters per second when it accelerates at 5 meters per second squared for 3 seconds. Find the distance traveled by the car during these 3 seconds. All right, so I'll just take it piece by piece. The car is traveling at 20 meters per second. That's my velocity. It accelerates at 5 meters per second squared for 3 seconds. I want to figure out the distance. So looking at my formula sheet, what can I use? Which of these has distance in it? Well, this one has distance, but it doesn't have acceleration. This one has acceleration, but it doesn't have distance. Right, it looks like it's going to be this one right here. So d is equal to vi times t plus 1/2 times a times t squared. Right, my initial velocity is 20 meters per second. My time is 3. It's 1/2 times negative, I put negative 9.8. It's supposed to be 5. My acceleration here is 5, not negative 9.8, because my object is not falling. Times 3 squared. All right, you put this in your calculator. 20 times 3 plus 0.5 times 5 times 9. Is that right? Yeah. 82.5 meters. Question number 10. A car starting from rest accelerates at 8 meters per second squared for 4 seconds. What's the final velocity of the car? All right, my car starts from rest, so I know its initial velocity is 0 meters per second. It accelerates at 8 meters per second squared, so my acceleration is equal to 8 meters per second squared. And my time is 4 seconds. I'm trying to figure out VF. What's my final velocity? So looking at this equation sheet, I'm looking for something that has acceleration, time, VF, and VI. Looks like this one or this one actually. Look at there. This says VF is equal to VI plus A times T. And it's really just a rearranged form of this one up here. Alright, so if you're accustomed to using this equation, go ahead and do that. But this one gives it to you straight out. So we're going to say VF is equal to VI plus A times T. So that's equal to 0 plus 8 times 4 equals 32 meters per second squared. Coolio. Number 11. Oh, it's the penny problem. A penny is dropped down a well and takes 5 seconds to hit the water at the bottom. Find the distance the penny fell and the velocity with which it hits the water. So number 11, we have a penny, we drop it down a well, it drops for 5 seconds. Time is 5 seconds. It doesn't look like the problem gives you any other information, but you have to think back to the free fall unit, or the projectile motion unit, and remember, an object that is dropped has an initial velocity of 0. Also, if something is falling in free fall, on Earth, its acceleration due to gravity is going to be negative 9.8 meters per second squared. Great. So we want to figure out two things. We want to figure out VF, and what's the other one? The distance in the y direction. To figure out VF, we're just going to use the same equation that we used in number 10. So VF equals VI plus A times T equals 0 plus negative 9.8 times 5. I think that's negative 49. Let's see. Yep, negative 49 meters per second. That's how fast the penny's going after 5 seconds. To figure out the distance, I've already written this equation down, showing you which one. It's going to be distance is equal to your initial velocity in the y direction times t plus 1/2 times a times t squared. 0 times 5 plus 1/2 times negative 9.8 times 5 squared. So this term goes to 0. This stuff over here is negative 122.5. So my distance in the y direction is equal to negative 122.5 meters. Why is it negative? Because my object was falling down. Down is the negative direction. All right, number 12. A car goes 5 kilometers north, then the car goes 4 kilometers east. What is the displacement vector? Always draw pictures on these. It will help you figure out what's going on. So here's my car. It's a little point. It goes 5 kilometers north. And then 4 kilometers east. The question says, what is the displacement vector? Another way of saying that is, how far are you from where you started? Alright, and to do this we use the Pythagorean theorem. A squared plus b squared is equal to c squared. So we get 5 squared plus 4 squared is equal to c squared. Uh, 25 plus 16 is equal to c squared. 41 is equal to c squared. But our answer, we don't want to figure out what c squared is equal to. We want to figure out what c is equal to. So take the square root of both sides, and c is equal to the square root of 41 kilometers. Which direction? Well, I went north, and then I went east, so my direction is northeast. Number 13. You walk oh, this one is hard. We haven't done one like this before this review. You walk some distance north. Okay, so I walked north for a little bit, but I don't know how far. And then I walk 4 miles west. I am 5 miles from where I started. Okay, well, I'm right here right now. Right here. I started down here. What's the distance there? You just told us it's going to be 5 miles. Well, here I'm given this last part that we normally find for. This is called the hypotenuse to your triangle. I'm given the hypotenuse in one of the legs, I need to solve for another leg now. All right, well, C is always going to be what your hypotenuse is. So here, our a squared plus b squared equals c squared. 5 is going to go in place of the c. And 4 is going to go in place of whatever else you want it to. So 16 plus b squared equals 25. Subtract 16 over. B squared equals 9, which means that b equals 3. And which direction was this vector pointing? North. 3 north. All right, we'll do number 14 in this little space over here. Number 14. A cow walks 29 kilometers south. And then because she's a cow and cows are stupid, actually cows probably aren't stupid, I don't know, I've never met a cow. Okay, she turns around and she walks 10 kilometers back north. Oop. Alright, so we want to know what's the cow's displacement. Well, displacement, again, is how far you are from where you started. I'll write that out. Displacement equals how far from where you started. In this case, I started right here, right, and I ended up right here. But I want to figure out how long this distance is. I got to do 29 minus 10. And that gets me 19. I'm 19 kilometers from where I started. In what direction did I walk overall? I walked south. Or the cow walked south, sorry. Okay, number 15. Okay, describe the horizontal and vertical motion of a projectile. A few things you need to know here. The horizontal and vertical components are independent. What does that mean? That means if I have a gun right here, right? They watch this on Mythbusters. Here's a gun. It's going to shoot a bullet. At the same time, I'm holding a bullet right next to the gun. Okay? I'm going to fire the gun and drop this other bullet at the same time. Okay? Bang! And at the same time, this thing just starts falling. The bullet is going to take the shape of a projectile, right? It's going to still go out. It's still got a horizontal velocity, but it's going to fall, right? It's going to fall at the same rate as this first bullet. And we saw that because the bullets hit at the same time. Even though the bullet fired from the gun had a huge horizontal velocity. Its horizontal velocity didn't affect how it fell. All right, so that's why horizontal and vertical components are independent. Other thing you need to know, for the horizontal direction, your initial velocity is going to equal your ending velocity. Okay, so if my bullet that I fired here started out with a horizontal component of 800 meters per second this way, right before it hits the ground, it's also going to have a horizontal component of 800 meters per second. Okay, these numbers don't change. What does that mean? The acceleration in that direction is 0. The velocity of the horizontal doesn't change, so the acceleration's got to be 0. That's not the case for vertical. Why? Because gravity changes the velocity of vertical. I should say it changes the vertical velocity. Let's put that there. Gravity changes the vertical velocity. Alright, so in what way does gravity change it? The acceleration, gravity changes the velocity of an object every second by negative 9.8 meters per second. So the acceleration is negative 9.8 meters per second squared. Alright, moving on. Number 16. How is mass different from weight? Mass is the amount of stuff that makes up an object. Okay, it's how much stuff makes up an object. Weight is equal to the force of gravity an object feels. Okay, these two are very much tied together. All of our experience of mass has to do with weight, right? If you want to know how massive something is, you got to kind of figure out how much does it weigh. But these are really different ideas. Weight is going to be a force, right? And it depends on you being on a planet or a moon or something like that. Mass is independent of location. So let me write that. Weight depends on location. Mass is independent of location. Wherever I go in the universe, I'm still going to be made up of the same amount of stuff. But the gravitational force that pulls on me is going to change depending on the planet that I'm on, or the star that I'm next to, or the moon that I'm orbiting. Alright, number 17. A 65-kilogram astronaut travels to the moon. I feel like this is a different review than we have. I'm not sure if you guys have this question. A 65-kilogram astronaut travels to the moon. On the moon, his mass would be more than 65 kilograms, less than 65 kilograms, or equal to 65 kilograms. I remember seeing this worded differently on the sheets that I passed out. But I'm just going to move ahead, hoping that all the questions are the same. Alright, so if the astronaut's mass is 65 kilograms on Earth, well, mass doesn't change, right? So it's going to be 65 kilograms on the moon. Number 18. I have a 100-kilogram object, or no, I'm sorry, a 100-Newton object on the Earth, and another object that weighs 100 newtons on the moon. Which object has a larger mass? Okay, let's think about this for a second. 100 newtons, so 100 newtons is a measurement of the force of gravity. All right, how much weight do these packages have? Well, the moon has less gravity, so it's got to be a bigger package in order to pull with the same amount of force. So the package on the moon is going to have more mass. Another way you can think about it is if you took the package on the moon back to Earth, what would its weight be? Would it be more or less than 100 newtons? It would weigh more because the force of gravity is going to be more. All right, number 19. A A truck is towing a trailer of the same mass. If the trailer is released, how will the acceleration rate for the truck change? So I'm just going to give you guys an example. I'm not... Alright, here's you. Not a very good drawing, I'm sorry. And here's you giving your sibling, your little sibling, a piggyback ride, okay? You're walking along, but you can't go very fast, right? If you drop your sibling, make them walk themselves. Let's see, here's you. You're able to go a lot faster now because you don't have that extra weight to carry. That's the same thing with the truck and the trailer. The truck is hauling the trailer. He can't go very fast. If he gets rid of the trailer, his acceleration is going to increase. Okay? So let's say if mass goes down, the acceleration goes up. And in this case, in all of these cases, the force stays the same. Next question. Number 20. A ball with a weight of 50 newtons is dropped. The ball encounters an air resistance of 20 newtons. What is the net force? Okay, net force is found by adding up all the forces, right? So the first force that we have to consider is the gravity force down. That's 50 newtons down. Hey, Dr. Bev, I'm doing a video right now. Like I'm live recording. It's cool. It's cool. Thank you. Thank you. Okay, sorry about that. So we're doing 50 newtons down and air resistance of 20 newtons. Okay, air resistance is always going to push in the opposite direction of your traveling. So this package is falling, right? Air resistance is going to push it up. So we got 50 newtons down of gravity, 20 newtons up of air resistance. When I add these two vectors together, what happens? I'm going to have to subtract because they're pointing in opposite directions.
All right. Happy holidays. Appreciate it. You too. Okay, thanks.
So my total force is going to be 30 newtons down. Net force, 30 newtons down. All right, I'm going to do number 21, and then I'm going to pause the video, upload what I got, and then keep going. So 21. An 800 Newton person is hanging from 2 vertical ropes. What is the tension in each rope? So here we go. Here's our, well, I'm not going to draw a picture really. We have a person, I'll just draw a box. They weigh 800 newtons. All right, there's a force down of 800 newtons. And they're being supported equally by 2 ropes that are pulling upwards. All right? The weight of the person is going to be equally distributed between the ropes. So 800 divided by 2 ropes equals 400 newtons per rope. It's as easy as that. If there were 3 ropes supporting this person, I would say 800 divided by 3, and so on. Number 22. Oh yeah, I'm going to pause it now.